In this discussion, we're going to focus on ways to represent electrons in the orbitals of an atom. There are a couple of rules that we need to look at that govern the ways that electrons fill the orbitals. The first one is the oftball principle. If you have completed the Hogg-Hilton activity, this is analogous to the rule that hogs are lazy. So electrons are always going to go into the lowest energy orbital that is available. And then they'll go to the next and the next and so forth. So when we are putting electrons into the orbitals, the first electron is always going to go into the 1s orbital because that's energy level 1, and the s-type orbital is the lowest energy in energy level 1. The other rule we're going to use is Hunds rule. Hunds rule is equivalent to the Hogg-Hilton rule that says that hogs don't like each other, and so when you're booking them into rooms, you have to give them each their own room if possible. And this rule applies to sublevels like P's, D's, and F's, where we have multiple orbitals that are of equivalent energy. And so what you'll see when we start actually drawing these out is that when we have electrons to go into a sublevel, like a P, for example, the first three, there's 3 P orbitals. So the first 3 electrons that go in, each one goes into its own orbital. And then if I have a fourth one I have to put in there, that one will double up with one of the others. Okay, orbital notation. Here we're going to draw, you'll see these sometimes with boxes or with lines. I like to use lines typically, but we're going to use a line for each orbital. And under the line, we're going to put the first and second quantum number for that orbital. And so if this were the lowest one, it would be energy level 1, and then S would be the orbital type. Okay, and with Hunds rule, all right, we're going to use arrows for the electrons in orbital notation. And so this one is talking about Hunds rule. So say, for example, here's our 3 orbitals, and say these are the 2p orbitals, all right? And since we have multiple orbitals, we're going to designate these X, Y, and Z just to differentiate between them. And so say I have 4 electrons that are going to go into this sublevel, the 2p sublevel. Well, I would do 1, 2, 3, each in its own orbital, and then on the fourth one, that's where I'm going to double up. You'll notice that when I doubled up on there that I drew the arrows in opposite directions. And this represents the fact that electrons in the same orbital have to have opposite spins. So that's how we show that. Electron configurations, rather than showing every individual electron, here it's more like a summary of how many electrons are in each sublevel. And so for that, we're going to have the first or principal quantum number, the letter that represents the second quantum number, and then we're going to superscript with the number of electrons that's in that sublevel. All right? And so, as an example, here we have 1s2, 2s2, 2p5. So that means in the 1s sublevel, I have 2 electrons. In the 2s, I have 2 electrons. In the 2p, I have 5 electrons. Okay? If I were drawing out, say, the orbital notation that was equivalent to that, I would have a 1s, a 2s, 2p, it's an X, Y, and Z. And so we have 2 in the 1s, 2 in the 2s, and then 1, 2, 3, 4, 5 in the 2p.